Hello, welcome. In this session of our tutorials, we would be looking at this question of GCE 2020 for the mathematics paper 3, and it was question 1. The question is from the topic modeling with differential equations, and it says a particle P is projected vertically upwards from a point O with speed 2g over k meter per second in a medium whose resistance to motion is of magnitude kV per unit mass, where v is the speed of P and k is a positive constant. 1. Show that v dv dx equals negative g minus kv for 1 mark. The particle P attains the highest point h of its path. 2. Show further that OH equals g over k into 2 minus ln 3 meters for 5 marks. Given that the particle reaches another point m with speed g over 2k meter per second as it traces its way back to O, the point of projection. 3. Prove that hm equals g over k squared into ln 2 minus half meters for 4 marks. Okay, we begin the solution straight away, but it's important to note that for questions that involve modeling with differential equations, you are going to be relying very much on integration. And it's important that we look at some standard formulae or some methods of integration which will be very crucial in this question. We have first the integral of 1 all over ax plus b dx, and this integral generally always comes from this general case which has the integral of a rational function such that f prime of x is divided by f of x. When this happens, the integral is simply ln of f of x plus the constant of integration. So if we take this integral, we have this would be the integral of, now the derivative of the denominator is a. So when you differentiate a linear function, you are just left with the coefficient of x. Ax plus b is a linear function, and for us to apply this format, we need that the derivative of the denominator should appear at the numerator. So I introduce a, I multiply the numerator by a, then I have ax plus b at the denominator, and then I compensate with 1 over a in order that the a that is multiplied would be neutralized. So when that happens, now we have 1 all over a ln of the denominator as the integral plus the constant of integration. We also have the situation where you might have x all over ax plus b. So this was the first case. The second case, x all over ax plus b dx. And in this case, you can see that it's different from the first. The numerator is no longer a constant, but the variable x itself. When such a situation appears, you have a linear function at the numerator and a linear function at the denominator. There is the need to do partial fractions before you can be able to integrate. In this case, the best strategy would be to make sure that the linear function at the denominator appears at the numerator. So I will start by multiplying the numerator by a so that I build up to determine x at the numerator. So I multiply the numerator by a so that I get ax. Then I neutralize that multiplication by multiplying the integral by 1 over a so that the a can always cancel and the function will not be altered. So I then divide by ax plus b. From here now, 1 over a will multiply the integral of ax. Since I need that the numerator should be exactly like the denominator, we have ax plus b at the denominator, and at the numerator we just have ax. So I would add b and perform the reverse operation of addition, which is subtraction of that same b, so that again the function at the numerator is not altered. From then I have 1 over a integral of, I will now distribute the numerator. These first two terms will be divided by the denominator, while negative b would also be divided by the denominator. So we get ax plus b over ax plus b, which is 1 minus b all over ax plus b. And this now is easier to integrate, so that we have that the integral of x all over ax plus b dx would be 1 all over a into the integral of 1 with respect to x is x minus. So generally this term again resembles the first integral that we were just from C, and I need to divide the constant term at the numerator by the derivative of the denominator, which is a, and then ln of ax plus b, and then plus the constant of integration. There is another formula, the standard one, which you would surely have in the formula booklet, which is the integral of 1 all over a squared plus x squared dx. This one is in the formula booklet, and when it appears, you simply take 1 over the square root of the constant term a squared, which will just be a, and then tan inverse of x over a plus the constant of integration. So these three formulae are very useful when we are performing integrals that occur in the solving of problems under modeling with differential equations. So as an exam strategy, once you're solving a problem under modeling with differential equations and you come across any of these standard integrals, you can proceed to state the ones that I have highlighted and then proceed to apply them. The constants that will be involved may not be a and b again. Most of the time, a is a certain k and b is g, the acceleration due to gravity in such questions. So the best practice in order to save time and be convincing in your solving is to proceed and state any of these standard formulae with the constants in terms of a and b, and then proceed to replace a by k and b by g so that you can proceed with your solving smoothly. So going back to the question, it says the particle is projected vertically upwards from a point O with speed 2g over k in a medium whose resistance to the motion is of magnitude kV per unit mass, and v is the speed and k is a positive constant. So the motion in this question is calculated in two phases. There is the first phase where the particle is moving vertically upwards and is projected with a certain speed 2g over k, and then the second phase will be when the particle is on its way down to O where it was first projected. Okay, we start with the first part. In the case where the motion is vertically upwards, if the particle is moving vertically upwards, then we have the weight of the particle as one of the opposing forces. Weight should be mg, and then there is the resistance of the medium, call it r. So there is no forward force pulling the particles forward due to the fact that the initial kinetic energy that the particle is given would be providing that forward motion until at a point where the velocity will reduce to 0 at the maximum point, where it will now come to momentary rest. So for this first case, we have the acceleration upwards in this direction. We are told that the resistance per unit mass is kV. So if R over M is the resistance per unit mass, then we can equate it to kV, so that R would be equal to m kV. So now we proceed to apply Newton's second law in the upward direction. And in the upward direction, we have that the leading force there is 0, and the opposing forces are mg and r, and that should be equal to the mass times the acceleration according to Newton's second law. We then have that negative mg minus r is mkv, as we just found it up here, and that should be equal to ma. The m's would cancel from all the terms, and we then have that a equals negative g minus kv. Now a is the rate of change of velocity, which is supposed to be dv dt, and by the chain rule we can also write that dv dt is equal to dv dx, where x is the distance moved by the particle, times dx dt. And from here we have dv dx times dx dt. Rate of change of displacement is supposed to be the velocity or the speed. So we are saying that a would also be written as v dv dx. So we have now that the equation that we had up as a equals negative g minus kv will become v dv dx equals negative g minus kv as required. We're asked to show in the first part that v dv dx equals negative g minus kv. It should be noted that the solving is long, because you should be wondering why it's 1 mark and I've written so much. It's just to make sure that you follow up the steps and understand what is happening. Normally, at the stage where you have a equals negative g minus kv, you are just supposed to replace a by v dv dx, and you arrive at your statement that you are required to prove. In the second part, we are told that the particle p attains the highest point h of its path. Show further that OH equals g all over k squared into 2 minus ln 3 meters. So in the second part, we are going to take the statement that we are just from proving, v dv dx equals negative into g plus kv. I have factorized the negative on the right hand side. Differential equations of this form are solved by integration, as I already said. So we start by cross multiplying and then separating the variables. So we have v dv equals negative into g plus kv times dx. Now this term in brackets is in v, and the variable v is on the left hand side. So I will divide both sides by that bracket so that I will separate variables successfully. So v dv all over that bracket g plus kv would be equal to negative dx on the right hand side. Then I integrate both sides, and on the v side I will be integrating from the initial speed that the particle was given, which is 2g all over k, and on the distance side I will be integrating from 0 because initially the distance of the particle from O is 0. Then when the particle reaches the maximum height, the velocity or the speed would be 0, while the distance moved would be the distance from O to H, where the maximum height is, so the distance OH that we are seeking to find. From here we have that integral from 0 to 2g all over k of v dv all over g plus kv should be equal to integral from 0 to OH of dx. So there was a negative sign on the right hand side there. Each time you have this case of the particle moving vertically upwards, there is always a negative sign somewhere. According to one of the properties of definite integrals, the negative sign can always disappear when you switch over the limits. You change the lower limit to become the upper and the upper to become the lower. That is what has been done on the left hand side. It was from 2g over k to 0. Now it is from 0 to 2g over k. So that is to avoid mistakes that usually come with the handling of negative signs when you are solving. On the left hand side, the integral is identical to this one that we just derived. The integral of x all over ax plus b dx is equal to 1 all over a into x minus b all over a ln of ax plus b. And then plus the constant of integration. So as I said, if you can follow up with the method of partial fractions that I did, you can always follow up with that and integrate this case where v appears at the numerator and at the denominator, then it's fine. But where you cannot master it, you go straight each time it appears and you state this formula, say from this integral. I would proceed directly with the left hand side and replace every a by k and every b by g in that integral that I am supposed to do on the left hand side. So that integral will be equal to, and now apply this right hand side of the standard integral derived, which will be 1 all over k being replacing the a now, into the variable x is replaced by v because we are now dealing with v, minus g, which is replacing the b, all over k, which is replacing the a, then ln of g plus kv, the denominator. And we are integrating from 0 to 2g over k. That should be equal to the integral of dx is simply the integral of 1 with respect to x, which will give us x, and we are taking from 0 to OH. On the right hand side, the substitution of the limits gives OH minus 0. So we have that OH, which we are seeking to find, would be equal to 1 all over k into v, and v, we are substituting now the upper limit for v, which is 2g over k. So v is replaced by 2g all over k minus g all over k ln of g plus k into 2g over k. That is the substitution of the upper limit minus 1 over k into the substitution of the lower limit, where v is 0, so we have 0 minus g all over k ln of g plus 0 kv, and v is 0, so we have g plus 0. So we have that OH equals 1 all over k into 2g all over k minus g all over k. Ln of g plus k cancels here, and we have ln of g plus 2g. That gives 3g minus 1 all over k into negative g over k ln of g. In this last term, the negative times the other negative will give positive. So we can make that bracket to be positive. Then we have in all the terms in the brackets, there is g over k that is common. So I have 1 over k into g over k, and then into, we divide every term in the brackets by g over k. So we get 2 minus ln of 3g, and then plus ln of g, as we have factorized g over k from all the terms. Then we have g all over k squared into 2. Here we have ln of g minus ln of 3g. So we can write it as plus ln of g minus ln of 3g. And when you are subtracting two logs, you can combine and divide. So we have ln of g all over 3g. We're dividing the positive one by the negative one. So we have this, so that we get g all over k squared into 2 plus ln of 1 over 3. And we can then conclude that OH equals g all over k squared into 2 minus ln of 3 as required. Remember that ln of 1 over 3 is the same as ln of 3 to the negative 1. And the negative 1 can always spring to multiply the log according to one of the laws of logarithm. So ln of 1 over 3 is the same as the negative of ln of 3. Now in the last part of the question, we are given that the particle reaches another point M with speed g over 2k meter per second as it traces its way back to O, the point of projection. We are now required to prove that hm, the distance from the highest point to that point M below the highest point where the particle is descending, equals g all over k squared into ln of 2 minus half meters. So in the third part, direction of motion has changed. We now have the weight as the leading force, and the resistance of the medium is now acting vertically upwards. So the acceleration is vertically downwards. Applying again Newton's second law of motion in the vertically downward sense, we have that mg, the leading force, minus the resistance m kV should be equal to ma. The m's will cancel, and we have that g minus kV would be equal to v dv dx, the expression for acceleration in terms of v and x as we saw earlier. So in this case, we are replacing a by v dv dx because the question, that part, still involves the distance moved at when the velocity is a certain value given. So we still have v and x involved in the calculation. Otherwise, if the question involves velocity and time, we'll then replace a by dv dt. Again, we cross multiply in order to separate variables, so that we have g minus kv dx equals v dv. And from there, I divide both sides again by the bracket in v, so that I have dx equals v dv all over g minus kv. And again, I have to integrate both sides. Now, in this case, again, I need to be careful in determining the limits of integration. Initially, the displacement again from the maximum height where the particle is starting the descent would be 0, and the initial velocity at that maximum height would be 0 momentarily before it starts the descent. Then at a time when the velocity or the speed of the particle at m is g over 2k, the particle must have moved a distance from the maximum height equivalent to hm, the distance that we are seeking to find. So the integral of the left hand side, the integral of dx, is the integral of 1 with respect to x, which will simply be x, and we're taking from 0 to hm, and that should be equal to, on the right hand side we have again v dv all over g minus kv. We are still going to use this integral, Again, I said it's not in the formula booklet, so if you can master it so that anytime you have this case of integrating a linear function of v both at the numerator and at the denominator, then you can make use of it to save time and also the complications that might be involved in expressing it as a partial fraction. So from the integral of x all over ax plus b dx, which is supposed to be 1 all over the coefficient of x at the denominator into x minus the constant term, which is b, over the coefficient of x, which is a, ln of the denominator. We now have that the integral of v all over g minus kv dv would be equal to, I simply replace every b in the formula by g and every a in the formula by negative k. So I have 1 all over negative k into the variable x will be replaced by v, so v minus g all over negative k ln of g minus kv, the denominator. So in our integral we have the substitution on the left hand side of 0 to hm equals the integral of the right hand side that we have established, which is negative 1 all over k into v, negative times negative will become positive, g over k ln of g minus kv, and we are taking from 0 to g all over 2k. So the substitution of the limits on the left hand side will just give us hm minus 0, which is hm equals, substituting the upper limit g over 2k, we have negative 1 over k into g over 2k plus g over k ln of g minus k into g over 2k minus 1 over k, substitution of the lower limit, v is 0, plus g all over k ln of g minus 0 since v is 0. We then have negative 1 over k into g over 2k plus g all over k ln of g minus g over 2, since the k's will cancel, gives g over 2 minus minus becomes plus 1 over k into g all over k ln of g. Now expanding to remove the brackets in all the terms, we have negative g all over 2k squared minus g all over k squared ln of g over 2 plus g over k squared ln of g. All the terms have g all over k squared, so we factorize g over k squared into, we divide every term by g over k squared, we get negative half minus ln of g over 2 plus ln of g. This will give g over k squared into negative half. Then we have ln g minus ln of g over 2, that is positive the ln of g divided by g over 2, and that gives g all over k squared into negative half plus ln of g will cancel and 1 over half is 2. So we have that the distance hm equals g all over k squared into ln 2 minus half as required. We were asked to prove that hm equals g all over k squared into ln 2 minus half for format. Thanks for watching. If you are new to this channel, please consider subscribing and activating the notification bell so that anytime I post a new video, you will get the notification and then watch.